Picking up where we left off in section 6.1, we previously talked about finding antiderivatives when you're given a single term, like 2x squared, or negative x to the fifth over 5. Now we're going to talk about when you're taking an antiderivative with more than one term involved. So for instance, when we took the derivative of 5x squared minus 1, we have two separate terms that are being subtracted. We need to be able to reverse that with an antiderivative. So our rules say, given the integral of f of x plus g of x, all with respect to x, so dx on the outside of all of this, we can break this up into two separate integrals being added. So if you're adding inside of the integral, you can add two separate integrals on the outside. The same thing is true for subtraction. The integral of f of x minus g of x dx is equal to the integral of f of x dx minus the integral of g of x dx. Alright, so now we know that just like derivatives, we can take antiderivatives of each separate term that's being added or subtracted. And the last thing we should note is the antiderivative of e to the x dx is equal to e to the x plus c. Remember when we found the derivative of e to the x, we said its derivative is just e to the x. Well, that means the antiderivative of e to the x must also be e to the x. But there may be some constant value c added to it. Okay, so continuing on from there, let's go ahead and try an example. We have the integral of 2e to the x minus 4x cubed dx. The first thing we can do here is separate this because we have subtraction. We'll get two integrals, the integral of 2e to the x dx minus the integral of 4x cubed dx. At this point, notice that we now have constants that are being multiplied inside of each antiderivative. We'll talk about how to leave those inside in probably a few examples from now. But as of right now, we still want to take them out of the integral. So we will pull the 2 out and the 4 out, giving us 2 times the integral of e to the x dx minus 4 times the integral of x cubed dx. And now from here, we can start taking our antiderivatives. We have 2 times the antiderivative of e to the x. Well, we said that's just e to the x. It doesn't change, but we do get a plus c. Minus 4 times the antiderivative of x cubed gives us x to the 3 plus 1 over 3 plus 1. Again, we add 1 to the exponent and divide by the new exponent. Plus c again. Now technically, you should write c1 and c2 here, but it all ends up becoming c anyway, as we discussed in the last video, so we don't really need to worry about that. They're just some constant values that'll all get condensed into 1. So by distributing the 2 and the negative 4, we end up getting 2e to the x plus c. Again, remember the 2 doesn't need to be distributed to the c. And we get minus 4 times, we need to simplify this. We have x to the 3 plus 1 is x to the 4th over 3 plus 1 is 4. And then negative 4 times positive c again leaves us with c because the constant will not change. And from here, notice that we have 4 times x to the 4th over 4. If it helps you to think about it, when you're multiplying fractions, you can put anything over 1. And now hopefully it's easier to see we have a 4 in the top and bottom, and because we're multiplying, we can cancel that 4 out. So that leaves us with 2e to the x minus x to the 4th plus c. Again, it doesn't matter how many numbers, that is constants, we have multiplied to c. It doesn't matter how many c's we have added together. They will still always end up just being plus c in the final answer. The last problem we go through in this video will finally confirm why that's true. So from here, this is a bit of a difficult problem, but I would like you to try to pause the video and see if you can come up with a way to find the antiderivative of 4x to the 6th plus 2 all over x cubed dx. Okay, so we're going to go ahead and try it from here. Remember, we have division going on, and we haven't introduced an antiderivative rule for division. So to handle this, we need to get rid of the division, which we can do by either splitting up the addition in the numerator into 2 separate fractions being added together, or by taking this x cubed and multiplying it to the numerator with a negative exponent. So we have the antiderivative of x to the negative 3rd times 4x to the 6th plus 2 dx. It's being multiplied to the entire numerator because it was dividing the entire numerator originally. And when we distribute this x to the negative 3rd, we have the integral of 4x to the, we are multiplying with like bases, so we add the exponents. Negative 3 plus 6 gives us positive 3. So we have 4x to the 3rd plus 2x to the negative 3rd dx. And we need to put parentheses around these terms. And now we can take our antiderivative because the division is gone and the multiplication in this step is gone. So, at this point, we could break these up into 2 separate integrals, just like we did in the last problem, or we could keep them together. For this one last problem, I'm going to show keeping them separated, and then from then on, I will show the shortcut of how to do it, keeping them all in one integral, just like we would handle a derivative. So, one last time, to take care of addition inside of an antiderivative, we break it up into 2 separate integrals. We have the integral of 4x cubed dx plus the integral of 2x to the negative 3rd dx. And now that we've separated it, like I was just saying, we can show how to do this without taking out the constants like I had mentioned in the last problem. So think about when you take the derivative of, let's say, 2x to the 3rd, for instance. When you do this derivative, you don't take out the 2 and then start finding the derivative of x cubed. Technically, you can, and that's how you typically would first learn it, but as you progress through learning derivatives, you know you can just leave it right where it is and multiply the exponent to the 2 and subtract 1 from it to get 3 times 2 is 6. X to the 3 minus 1 is 2. We can do the same thing with antiderivatives. We don't have to take this 2 and this 4 out of the integral. You can, but it's not necessary. You can leave it right where it is and take your antiderivative, meaning 4x to the third, to find its antiderivative, remember we add 1 to the exponent, and then we divide by the new exponent, and that 4 is just staying multiplied to the x as it started in the problem. Here we have plus the antiderivative of 2x to the negative third. We have 2x to the negative 3 plus 1 all over negative 3 plus 1. It is worth noting that with each of these, there should be a plus c. I hope that's not too small to see there. It's just a plus c I'm adding in. And then again, a plus c again. And when we do this, we get 4x to the fourth over 4 plus c plus 2x to the negative 2 all over negative 2 plus c again. We'll start simplifying. 4 divided by 4 will cancel out. 2 divided by 2 will cancel out, though we have to remember that negative is still there in the denominator, and we'll have to move it up to the numerator. So we get x to the fourth minus, because of this negative in the denominator, minus x to the negative 2 plus c. Remember, no matter how many of these c's you have, you still leave it with plus c, just plus one of them in the answer. And from there, we finally bring x to the negative 2 down to give us x to the fourth minus 1 over x squared plus c. Now that we've gotten rid of the negative exponent by bringing it down, we have our final answer. At this point, we'll introduce another fact that says the integral of 1 over x dx is equal to the natural log of the absolute value of x plus c. Think about why that's the case. Remember, if you were to take the derivative of this, you should end up getting what's inside the antiderivative. What's the derivative of the natural log of x? Well, that's just 1 over x. The reason we have to include these absolute value symbols, though, is because this antiderivative didn't start with a natural log inside of it. And because it didn't start with a natural log inside of it, it's perfectly okay to have negative x values. But remember, you cannot plug a negative x value into a natural log. So we put these absolute values to say we need to be careful about our domain. This way we don't get any undefined answers. It is also worth noting that x cannot equal 0, because you also cannot plug 0 into a natural log. So going through this in our next example, we're taking the antiderivative of minus 3 or negative 3 e to the x plus x squared plus 1 over x. So like I said, for this example, I am not going to break it up into multiple terms that are multiple integrals, that are being added or subtracted, showing how, just like you can leave multiplied constants inside of your integral when you take the antiderivative, You can do the same thing with addition and subtraction, and just take the antiderivative of each term separately. Before we get started though, we do need to simplify one thing, and it's this fraction. We can't take the antiderivative of a fraction that has a variable in the denominator, because that's basically taking the antiderivative or derivative of something that might have involved the quotient rule. So whenever you see something that has multiplying or dividing, it means that you're reversing basically the quotient rule or the product rule, and we haven't learned how to do that yet. So we have to get rid of this fraction, and we could do that one of two ways. The first is we could bring this x up with a negative exponent like we've done in previous problems. And another way that we could handle it is whenever you have addition or subtraction in the numerator, only in the top, you can break it up into multiple fractions, meaning you can take each term that's being added or subtracted in the top and put them all over the same denominator. Again, I want to emphasize this only works when the addition or subtraction is in the numerator. So we would get plus x squared over x plus 1 over x dx. Notice if we were to add these back together, we would get x squared plus 1 over x, which is exactly what we started with. And again, that only works if the addition or subtraction is in the top. From here, we'll simplify one more time. The integral of negative 3 e to the x plus x squared over x is just x. And then from here, we have plus 1 over x dx. And now we can take the antiderivative of each term separately. If you find this too complicated to handle, you can separate each one into a different integral, meaning the integral of negative 3 to the x dx plus the integral of x dx plus the integral of 1 over x dx. But this method will show you, just like when we handle a derivative, you can keep them all in one integral and just take the antiderivative of each term that's being added or subtracted separately. So, starting with the first one, the integral of negative 3 e to the x. Well, we know the integral of e to the x is just e to the x. And we know that if you're multiplying or dividing by a constant, that just multiplies or divides to your answer. So we get negative 3 e to the x for our antiderivative. We don't need to put the plus c here because we're keeping this all in one. From here we have plus x, the antiderivative of plus x, we get x to the, there's technically a 1 here, so x to the 1 plus 1, we add 1 to the exponent, and then we divide by the new exponent, 1 plus 1 again. Plus, the antiderivative of 1 over x, we just said, is the natural log of the absolute value of x. And then finally, we can put plus c at the very end. Just a note, if this were the antiderivative of 5 over x, you would get 5 natural log absolute value of x. Minus 10 over x, minus 10 natural log absolute value of x. Whatever number is in the top, you just multiply it to your natural log, as long as it's a constant. And now we'll just go ahead and simplify this. We have negative 3 e to the x plus x squared over 2 plus the natural log of the absolute value of x plus c. And that is the complete antiderivative of what we started with. So notice we didn't have to break it up, but what we did was the exact same process as if we broke it up. Just like when we take a derivative, for instance, of something like 5x cubed minus 3x. We don't need to break up the derivative notation to each term that's being subtracted. We know to just take the derivative of each term that's being subtracted separately. And the same thing happened here. All right, so from here, we have just a little bit left to go. First of all, we're going to introduce a couple of facts, and the first is if you have the integral of dx or the integral of 1 dx, either case it's the same thing, that will always be equal to x plus c. Think about why that is. If we took the derivative of x, we would just be left with the constant in front of it, which is just 1. And notice that's all that's technically inside of this antiderivative, 1 dx, or just dx. Likewise, the antiderivative of k dx is the same reasoning we just had for the integral of 1 dx, the integral of k dx, where k is a constant, is kx plus c. You take whatever constant is being multiplied to dx and attach an x to it. So the reasoning for that is, again, if you took the derivative of kx, where k is a constant, the x would just go away, leaving you with this k. So for that, let's go ahead and check an example. We have the integral of -2 dx. So what did we take the derivative of to get just -2? Well, we took the derivative of -2x. And then again, there is always the chance that we have a plus c. So no matter what, when you have a constant multiplied to your dx, the antiderivative is always that constant times x plus c. All right, so finally we're on to our last topic here. And this problem will help us find the exact value of c. And this will also explain why we can always just put this plus c here, and we don't need a plus 5c or a minus 6c1 plus 8c2. We can always just put a plus c there. So to explain that, we're going to start with this problem. We have if dy dx is equal to x to the n, meaning if your derivative is equal to x to the nth power, then if we were to take x to the n and put it over 1, it wouldn't change the problem. But by doing this, we now can cross multiply. And if we cross multiply, we would get dy times 1, or just dy, equals x to the n dx. And from here, let's say we want to solve for y. To solve for y given dy, we would have to take the antiderivative of each side. And although it might not seem intuitive that we can do that, notice that this is exactly the same thing that we started with in our first video on section 6.1. We said if you have two derivatives equal to each other, then their antiderivatives are equal as long as you account for that plus c, or that constant that comes when you take an antiderivative. So let's go ahead and do that. What's the antiderivative of dy? It's just y. We don't have to worry about the plus c because we've already put it on the other side of the equation. What's the antiderivative of x to the n? It's x to the n plus 1 over n plus 1. And we have now found an equation for y given the derivative of y with respect to x. So let's see how we can apply this in our next and final problem. We want to find the equation of the curve, meaning the original function, that passes through 2, 5 if the slope is given by dy dx equals 2x. So we're given the derivative dy dx equals 2x, and we want to find the original equation for y. We're going to use exactly what we just demonstrated in that last fact. We're going to take dy dx and set it equal to 2x and solve for y. We'll do that by putting 2x over 1 so that we have two fractions equal to one another, which allows us to cross multiply, giving us dy times 1, which is dy, equals 2x times dx. And from here, we can then take the antiderivative of each side, which will give us the antiderivative of dy is the y that we're looking for. And that's equal to the antiderivative of 2x gives us 2x to the, remember our exponent is technically a 1 here, so we have 2x to the 1 plus 1 all over 1 plus 1. And that's all plus c. So from here, simplifying, we get y equals 2x squared over 2 plus c, which leaves us with y equals, when we cancel these 2's out from the top and bottom, y equals x squared plus c. And finally, to solve for our c value to get the exact equation that we started with, we need to plug in the point that we were originally given. We know y is equal to 5, x is equal to 2, so 5 equals 2 squared plus c, which gives us 5 equals 4 plus c, and subtracting 4 from each side, we get c equals 1. So y equals x squared plus 1 instead of c is the original curve that the problem started with. Alright, so notice at the end of the day, it didn't matter what we labeled c as. It was still always going to be plus 1. No matter what value we would find, we would get c equals 1 at the end of the day. What I'm saying by that is, remember, on this step, the integral of 2x dx, I'm going to write this off to the left. The integral of 2x dx, when we first learned how to do that, we would take the 2 out, which gave us 2 times the integral of x dx. And then when we start taking the antiderivative of x, we would get 2 times x to the 1 plus 1 over 1 plus 1 plus c. And now hopefully you can see where I'm going with this. If we simplify, we get 2 times x squared over 2 plus c. And distributing the 2, we get 2 times x squared over 2 is just x squared plus 2c. What would have happened if we would have plugged in the point 2 comma 5 and we would have had 2c instead of the c that we had when we originally solved the problem? Technically, it should have been a 2c there, but we didn't write it. Well, let's see. We have y equals x squared plus 2c. If we plug in 2 comma 5, we have 5 for y equals 2 squared plus 2c. So 5 equals 4 plus 2c. Subtracting 4 from each side, we get 1 equals 2c. And at this point, it's important to stop, because we weren't solving for c. We don't care what the value of c is. We care what value is being added to x squared. We wanted to solve y equals x squared plus some number. We just found what that number is by finding 2c. It's 1. So when you plug that value of 1 back into 2c in this step, you get y equals x squared plus 1, which is exactly what we have here. It was just a more complicated way to go about it by leaving that 2 there. But at the end of the day, it ends up leading us to the exact same problem. So always remember, just put a plus c. You don't have to do anything else to it. It will get you to the exact same result.